Uh, Hi everyone. I'm Yitian. I'm a final year PhD student at the Northeastern, supervised by Professor Raymond Fu. And yeah, it's a great pleasure for me to present here. And thank you guys for joining this session. And also, I want to thank the professors for the wonderful presentation on the physical AI. So today I'm going to offer a little bit different perspective on this, because when we think about the vision of physical AI, we should also notice that eventually we will apply the system in the real world scenarios. So we'll have to ensure the system can be run like on edge devices like robotics or autonomous driving. So yeah, the efficiency of the AI system is very important. We have to make sure that this can be scaled down while maintaining the performance. So yeah, the topic I'm going to present today is scalable and efficient deep learning from understanding to generation. So today I'm going to introduce two of my previous work. The first one is on generative efficiency. So we develop a video tokenizer with really compact latent space for efficient generation. And the second topic is going to be perception efficiency. So in this way, we're trying to answer the question how to obtain the vision foundation models with minimal cost. Yeah. And I'll first introduce about the first work on generative efficiency. So this page shows the typical text-to-video generation framework with the latent diffusion model. So given a raw video, it will be mapped into the latent space with the encoder, and then we will apply the diffusion model on top of it, and then the decoder will map it back to the raw video space. So the diffusion model actually run in the latent space, and the compactness of the latent space will determine the efficiency of the diffusion pipeline. And here is the inference pipeline of the latent diffusion model. So we will have a random noise at the same dimensionality of the latent to serve as the input for the diffusion model. And yeah, when we talk about the efficiency of diffusion model, there are actually many great works working on these directions, and I summarize them into three folds. The first one is the architecture optimization. We could do things like linear attention or develop the efficient backbone to optimize this process. And also second would be the post-training compression. We could do like pruning or distillation or quantization to optimize the model. And also we could do the denoising trajectory optimization, where we can apply step distillation to reduce the number of sampling steps of the diffusion model. So these are all like the current existing solution to enable efficient video generation. However, like the diffusion model, we know that currently we usually use the DIT model. It's basically a transformer structure. And we know that the time complexity of the transformer is actually one square because of the attention mechanism. And the N here is the number of the number of tokens in the latent space. So which means that the compactness of the latent space actually determines the efficiency of the whole diffusion model. So if you can have a more compact latent space, then both training and inference on the diffusion model will be a lot faster than ever before. And what's more great is also compatible with the previous direction I just mentioned. So this is the conventional video autoencoder structure, which applied the symmetric encoder-decoder structure, and it is trained with the reconstruction objective. While it works perfectly with the typical 4x temporal compression, we find that if we want to increase the temporal compression rate to have a more compact latent space, there will be always trade-off between the compression rate and the reconstruction quality. So we think the fundamental reason is that the current conventional decoder does not have any generative ability. So whatever information loses in the latent space, you just cannot recover it back. So to address this issue, we propose to use the idea of generative decoder, where we can only retain just enough structure in the latent space, and the rest of the part can be synthesized with the generative decoder itself. Because we know that the current generative model is very powerful, like diffusion. It can do text to image or video generation, which means that it can basically generate generate from nothing. And so we want to leverage this ability to facilitate this, to have a more higher temporal compression rate. Yeah, and this is our framework So given a raw video, it will be encoded into two latent frames, and then we specially design a conditioning module to process the signal, and then this will be added to the noise version of the input video. And for the decoder, we simply use the standard DIT transformer block, and in the end, you will be do the unpatchification and get into the original video. And the biggest technical challenge here is that the DIT block is made of transformer structure, and it's actually very hard to generalize to different resolution and aspect ratios. So to address this problem, we specially design a conditioning module, which we inspired by the idea of implicit neural network. So here we use the siren network to generate the condition with by the content aware PE, so that this content aware PE will not only carry the content information, but also provide the positional information to the model itself, so that we don't not need to rely on the fixed positional embedding in the traditional transformer, and so that our decoder can actually generalize to different resolution and aspect ratios. Yeah, and for the empirical results, first we evaluate our methods at the typical 4x temporal compression, where we can observe that our proposed methods can achieve much better results compared to the existing state of our video tokenizers on different benchmarks. And for the qualitative results, when we compare with the current SODA methods, we can see that even the state of our method like MacVid, it will fail in the challenging cases where it has high motion dynamic videos, but our methods can still maintain the structure very well due to the generative ability of our decoder. And if you want to further increase the temporal compression rate to, let's say, 8x, 16x, or even the extreme case of 32x, then our advantage compared to the MacVid will be increased if you increase the temporal compression rate. And here we also have some demo results at the 16x temporal compression, where we can see that the MacVid will fails and exhibits a lot of like flickering in the reconstructed video, while our method can still maintain the spatial temporal structure very well due to the generative decoder. And for the 32x results, it's the conclusion is similar. So MacVid will exist a lot of artifacts, while our methods will looks almost like the ground truth. Yeah, and also as I mentioned, the biggest technical challenge is that the DIT model is hard to generalize different resolution. So here we compare our methods with the conventional in-context conditioning, where we can see that the in-context conditioning model will exhibit the gradient artifacts when it's generalized to larger resolution or unseen resolution during training. But our methods can do perfectly and without these gradient artifacts. And another biggest concern of using the diffusion model as the decoder is that we know that diffusion model would requires a lot of sampling steps to achieve the good performance. However, in this project, we surprisingly find that our method can naturally support one-step sampling without any distillation. So here we have the results with our diffusion decoder to do sampling at different sampling steps, where you can see that our one-step results almost looks perfect compared to the reference results. And it's the difference compared to the 100 step is there will be almost like no visual difference. So which means that our method naturally supports one-step sampling, and it can be run as efficient as the conventional decoder. Yeah, and in the end, we apply our methods on our video tokenizer with 32x temporal compression for the text to video generation. So we train the model with 5 billion parameter model, DIT model, and here is the visualization results. So this part demonstrates that our extreme compact latent space can still do video generation. So that's about our first word. And the second word I'm gonna introduce is accessing vision foundation model via ImageNet 1K. So basically, in this project, we are trying to answer the question with how to obtain the vision foundation model efficiently with minimal cost. So vision foundation model is actually quite a heated topic in computer vision domain in like 2 or 3 years ago. For example, there are many great models like Clip, DynoV2, OpenClip, and SynClear. So this model has demonstrated remarkable generalization ability due to its large-scale training data and its self-supervised learning objective. And while this model have exhibits like surprising results, they also pose great challenging especially for the academia domain, because these models does not their training data is private, and also even if we have access to their data, it requires massive computation, which makes almost impossible for us in the academia to reproduce their results. So that we can only use whatever model they offer to us, and we have to use the original architecture because we have to use their pre-trained weights. So yeah, in this work, we are trying to answer the question of whether we could obtain the foundation model while maintain its generalization ability without using its original data. So a straightforward solution to this problem is using logic distillation, because we already have the pre-trained weights of the foundation model. But all the previous distillation methods, they mainly focus on task-specific problem. Well, in this project, we focus more on whether we can actually learn the original representation of the foundation model, and while maintaining its generalization ability. So our idea in this project is very simple. It's to decouple the foundation model from the massive data. And so for the data sets, we sort of think of it as the public anchor. So instead of as optimizing the model on the training data itself, we're sort of using as a tool or anchor point to use it to transfer the knowledge from the foundation model to our customized student model. So we're not trying to like optimize the model, its performance on this specific data, but we're using as a tool to align the representation from these two models. And for the learning objective, we have developed like 3 levels of objective, which concludes token level objective, patch level, and also future level objective. So those are very comprehensive, and it's very general because previous foundation models, they have quite different learning objective, but we surprisingly found that our proposed objective can cover all those objectives and can be generalized to different model. Yeah. And then I will show the empirical results. So first, we apply our methods on the foundation model DynoV2. So basically, we are using DynoV2 as the teacher and to align the representation with the data from ImageNet 1K, which only has 1.2 million images, while the original DynoV2 model is trained on 142 million images. And after the alignment, we evaluate our method on different tasks. So first, we do linear probing on the original ImageNet dataset, and we can achieve quite similar performance with the DynoV2. And further, we conduct experiments on 12 fine-grained classification datasets, and notice that many of those classes are not appeared in the original ImageNet. So here we are trying to verify whether our representation is actually aligned with the foundation model, and whether it can has those great generalization ability of those foundation models. And so here we have the average accuracy on those 2 scales. So for the BIT-based model, we have a small gap with the DynoV2, but it's already really great compared to the previous existing foundation models. And we have to consider that we only use 1.2 billion image to achieve this remarkable results, while those previous model achieve like using tons of images. And if we further increase the scale to the very large model, then we can surprisingly find that our performance is almost the same as the original Dino V2, which is the theoretical upper bound of our performance. So this part demonstrates that our methods can, although it's very simple, but also very effective and can be applied on the Dino V2 to have these remarkable results. And also, I mentioned that the foundation model has a really great generalization ability. So instead of only doing experiments on classification datasets, we also extend our method for dense prediction tasks like semantic segmentation and depth estimation. So we found that the conclusion is pretty similar with the previous page. Our methods can still achieve very close results compared to the Oracle results, Dino V2. And here we'll also do the visualization on the feature map of our method. And we found that our representation in NERM is very similar to the foundation model itself, although we didn't use any of its original training data. And what's more importantly, our method has really great generalization ability because our proposed proxy task is very general. So we directly apply our methods with two other foundation model, which is the SynClear, which use the contrastive learning objective on the 600 million datasets of synthetic images. And also we apply on the CLIP model. And we find that our the distilled students can actually obtain very close performance with the original teacher. And it's the curve almost looked at the same as the original model. So which means that whatever the distilled model is actually looks very similar to whatever we give it as the teacher model. So this further demonstrates the great generalization ability of our method. Yeah, and that's all for my presentation.